Hello and welcome to today's lecture. We are in our lecture notes, and last time we learned, we are in the chapter about Hilbert's 17th problem. So the topic is non-negative polynomials, and by non-negative I mean mainly globally non-negative, right? For example, a polynomial over real numbers in several variables, which is non-negative on the whole of R to the n. And so we are looking for sums of squares representations, for example, as a sum of square of polynomials or a sum of squares of rational functions of such polynomials. And we started in section 2.1 with non-negative polynomials in one variable over real numbers or over a real closed field, more generally. And we saw that they are sums of that they are always a sum of two squares of polynomials. And then here we saw that doesn't work if we for such questions it essentially doesn't matter if we work with homogeneous or non-homogeneous polynomials. So that was rather a technical section. Okay, and the next easy case would be to look at polynomials of low degree, right? Here we had polynomials in a low number of variables, in fact just one variable. And here we look at low degree. We look at several variables, but low degree. And degree 0, of course, is not interesting. Degree 1 is not really interesting, right? Because there are no non-negative polynomials of degree 1. That's easy to see. And then degree 2 is, of course, the next thing. So we look at polynomials of degree at most 2, quadratic polynomials. And also we will partially look at quadratic forms. That means we look at the homogeneous case, because it doesn't matter if you look at homogeneous or non-homogeneous. So quadratic forms, quadratic polynomials, non-negativity. What can we say about? And here everything will be very, very nice, again, like in the case of one variable, right? And later on we go to more difficult cases, right? So in 2.4 we will learn that not every non-negative polynomial is a sum of squares of polynomials. And in 2.5 we will learn that it is always a sum of squares of rational functions. And then here we will have a method how to decide whether a polynomial is a sum of squares of polynomials. So let's now go to today's topic. So we are here, non-negative quadratic polynomials. So let K together with less than or equal be an ordered field. Then if f is a polynomial over k in several variables, which is homogeneous, meaning that each monomial has the same degree, when f is called positive semi-definite, for short PSD, respectively positive definite, for short PD, over k, if f is non-negative on k to the n, meaning that f of x is greater than or equal 0 with respect to this order, for each x in k to the n, or if f is strictly positive on k to the n, well, without 0, right? Because at 0, the only chance that a homogeneous polynomial would be positive at 0 would actually be that it is constant, right? And but for non-constant homogeneous polynomials, they always vanish at the origin, of course. Okay, so we require this only except at 0. And if M is a symmetric matrix over K, when M is called PSD, respectively PD over K, if a quadratic form represented by M is PSD respectively PD. That means X transposed MX is non-negative for all X in K to the N. Respectively, it is positive for all X in K to the N without 0. You know, that's probably something you know, at least for the case where K are the real numbers, and you should know it from your linear algebra course, this definition. And now we have it here for an arbitrary ordered field, and it's exactly the same definition, right? But note that being symmetric is part of a definition. So if a matrix is PSD, when we require it to be symmetric, okay? This is something that students often forget. And yes, so for quadratic forms, this part A of a definition for quadratic forms, you probably have also heard it already, right? For quadratic forms. But okay, this is a generalization for arbitrary forms, for arbitrary homogeneous polynomials. So let K be, but let's now look at quadratic forms. Let K be a quadratic form over K in n variables. And now we require K to be Euclidean. That means that the squares form an order, right? When the following are equivalent. So Q is PSD in this sense, right? And Q is a sum of squares of polynomials. So I guess this was notation introduced in 1.1.18. It's a sum of squares of polynomials. And third, Q is a sum of n squares of linear forms. And the reference to 161a is just that's just where we said what we mean by linear form. Linear form is a homogeneous polynomial of degree 1, or it is the 0 polynomial. So it's a 1 form, right? Okay. And fourth condition, the signature of Q is the rank of Q. You know, the signature and the rank of a quadratic form was defined in 161H, where we had the following definition. So where K was also Euclidean. And that was, you know, we have shown that you can always write the quadratic form in this way as a sum of squares of linear forms minus the sum of squares of linear forms in such a way that these linear forms are all linearly independent, right? And then we had learned by Sylvester's law of inertia that the number S of squares here appearing positively and the number t appearing negatively, they are uniquely they are unique, right? They don't depend on such a representation. They are unique, and we call the rank S plus t, and that's actually that's actually the rank of a representing matrix. So. And we called S minus t the signature, right? So signature and rank together give the information on S and t, give exactly this information on S and t. So that was a reminder. Now here we say that signature of Q equals the rank of Q. That means there are no square in this difference of sums of squares. There is actually just a positive squares, right? There are no negative squares. So yes. Okay, so let's prove it. So from D to C, it's trivial, right? Because I said there are no squares appearing negatively. And from C to B is completely trivial. And from B to A is also trivial, right? Because I evaluate such a sum of squares of polynomials, then of course I get the sum of squares of elements in the Euclidean field, and that's of course non-negative. And Q is PSD, and all that remains to show is that we can go from A to D. Now suppose that D, so we show a contraposition, we show that if D does not hold, then we show that A does not hold. Okay, so if D does not hold, then, well, we learned that you can write Q as a difference of sums of squares of linearly independent linear forms. So let's do this, right? And now S minus T is the signature, but this is not equal to the rank, which is S plus T. And so we must have that T is greater than or equal 1, right? So there is at least one square appearing negatively. And now we want to use this in order to show that Q is not PSD. So that's quite easy, right? So we just have to plug in something where all the other linear forms are 0, and say one of these is non-zero. One of these ls plus 1 up to ls plus t is non-zero, and all the others are 0. So, and for this we use some trivial linear algebra. Let's look at this map, which maps an x to this tuple, which simultaneously evaluates all these linear forms. And now this is surjective. So maybe we copy this here. So this is surjective. Why is this surjective? Well, you know the rank. You know that all the LIs are linearly independent, right? So look at, for example, look at the representing matrix, right? If you think of a matrix which represents this linear map, you know you see immediately that the rows of this matrix are linearly independent, because you know, rows contain the coefficients of these linear forms, if you, right? Okay, so the coefficient tuples of these linear forms. So this matrix has rank S plus T, but that's also the dimension of the image of this map, right? Because that's also the dimension of a column space of this representing matrix. So it's surjective, right? Okay, so we can choose, and so if you take now this vector in K2 S plus T, this vector of length S plus T, with all zeros, but the last entry is a 1, when we find the pre-image x, and then Q of x is minus 1, right? It's 0, 0, 0, minus 0, 0, 0, minus 1. Minus 1 squared, which is 1. But minus 1 is smaller than 0, right? Okay. Good. And therefore Q is not PSD and A does not hold. Okay, so next proposition. Let K be a Euclidean field and M be a symmetric matrix n by n over K when the following are equivalent. M is PSD, there exists an S in N0 and an A in K to the S times n, such that M is A transposed A, right? So this A is an S times n matrix, and A transpose is when an n times S matrix. So it makes certainly sense to multiply these two matrices, right? And I mean, if you want, you could also say a positive integer here. There are some people who don't like matrices whose format is 0 times something or something times 0. But they are very useful actually, and they should be considered. But if you don't want it, then you could say S is a positive integer. Yes, and then so that means M is, you call that also Hermitian square. Some people call this an Hermitian square. It's not like A times A, it's not A squared, right? But you transpose the first thing when it's A transposed A. Or if it were a complex matrix, you would take a complex conjugate transpose. And then you call these things Hermitian squares sometimes. And then another thing is there exists an A in K to the n times n such that M is A transposed A. Right? So I could take here really a square matrix. And D, all eigenvalues of M, well, eigenvalues there, right? Because I'm just in this Euclidean field. So all eigenvalues, so I have to take a real closure of this Euclidean field, right? Important special case is that K is already real closed. In this case, I could here just take K, right? And so then I could just write all eigenvalues of M are non-negative, right? And the next condition is all coefficients of this. So that's kind of a characteristic polynomial, right? So a characteristic polynomial is, of a matrix is, usually is defined like this. When you get -1, if M is an n by n matrix, you get here -1 to the n, x to the n, and then, well, I guess plus -1 to the n minus 1 of, trace of M x to the n minus 1 and so on. And the last thing would be the determinant of M. Right? So that's maybe how you know it. Some people also define it like xin minus m, determinant of this. But when you get other problems, like when you could get here the plus minus 1 to the n determinant of m, so you get all these signs, right? You get all these sign issues, and of course the reason why you defined it here with a minus is that you wanted the eigenvalues to be its roots, right? But sometimes it's good to give up that requirement, right? And say that let's take a polynomial whose opposite eigenvalues are the roots, right? Such that the opposite eigenvalues are the roots. When I can just take plus here. When I don't know how to call this, maybe anti-characteristic polynomial. It's almost the same thing, right? And yes, and in fact, that's something I don't want to do now. But sometimes it can even be good to say that let's take a polynomial such that the reciprocal, the reciprocals of the opposites of the eigenvalues are its roots, right? So sometimes even this polynomial is better to consider, right? You don't know why, but if you generalize when if you want to define something like a characteristic polynomial for a tuple of matrices instead of just one matrix, then you will use several variables, and then you will write, so if you have m1, m2, two matrices, m1, m2, you could write x1, m1 plus x2, m2, and then plus the identity, right? So there are, in fact, it's not so clear that our definition of characteristic polynomial is the best one, and here I would actually prefer to work with this polynomial, which is up to some sign issues the same, of course, right? Okay, so so all coefficients of this polynomial are non-negative, right? Of course, you could express this in terms of the coefficients of a characteristic polynomial if you take care of the signs, right? That would mean that the signs alternate or something in the right way. Okay, and then if I write M in this way, then yeah, so the aij's are the entries of M, and when I take arbitrary subsets of 1 to the n, and I take that's called I guess a principal submatrix, right? I look at these principal submatrices where I keep the same rows and same columns, right? Indexed by the same numbers, and I delete all the other rows and columns, right? And I do this for every subset of indices. So I have 2 to the n choices here. It's quite a lot, right? And then I take here the determinant of these principal submatrices. That's also called the principal minors of a matrix, right? So I require all principal minors of a matrix to be non-negative, right? So you might have heard of a similar criterion, which we don't need right now, for positive definiteness, right? Instead of PSD, PD, you might know a similar criterion from maybe from your analysis course, or certainly, yeah, I guess from your linear algebra course, at least if you have heard my course. You know that for positive definiteness, there is a similar criterion where you look only at the leading principal minors. That means you just take subsets I, which are of a form 1, 2, 3 up to some number, right? So there are not a lot of leading principal minors, but there are a lot of principal minors. And for positive semi-definiteness, unfortunately, you have to consider all the principal minors, which are 2 to the n, which is quite a lot, right? So in this, to this respect, looking at this determinant is more convenient because it doesn't have so many coefficients, right? It has just n plus 1 coefficients. Okay. And yeah, let's prove these things. So a key thing is 2, 3, 2. 2, 3, 2, what we just did, right? So for quadratic forms, we have seen these equivalences, right? And now you know writing a quadratic form as a sum of linear forms, as a sum of squares of linear forms, we had actually a way of translating this into a statement about matrices, and that was probably 161e. So let's look at 161e again. So, okay. So that's here. So here we needed a field of characteristic different from 2, and we had a quadratic form. And when we said writing a quadratic form as a, well, here we had actually even weights. These weights, I think, are now +1 or -1. So we have Q is with weighted sums of squares. If and only if the representing matrix of Q is has this representation where the coefficients of the linear forms form the rows of P, right? Okay. So let's then see if you can use this. So I claim that A, B, and C, the equivalence of A, B, and C follows from the equivalence of A, B, and C above here, right? So the first thing is that, okay, so that's because this A here, so if M is the representing matrix of Q, so you could choose Q such that M represents Q, so you could, you know, so when M is PSD, if and only if Q is PSD, that's clear, and Q is a, a corresponding statement. So A is actually, so you have to be careful what we mean by that. So A is actually equivalent to A. B is, I guess, so yes, B is, you know, we use also 2.24c. So because if quadratic form is a sum of squares of polynomials, when these polynomials are automatically linear forms, right? That was here, right? If more generally, if a polynomial over a real field is a sum of squares of polynomials, then the squares here, these pi, are automatically linear forms, right? If D forms where D is half a degree of f, but now f is quadratic form, so they are automatically linear forms. Yeah, and that's why this blue statement here this one here, this one here, right, means actually that Q is a sum of squares of linear forms. And when I can translate this using, you know, my correspondence between writing a quadratic form as a sum of squares of linear forms and matrix identities, I can actually translate this in such a condition, right? If I write it here as a sum of S linear forms, when this translates into such a condition, right? The weights are all 1 then, of course, right? So there is the identity matrix in the middle, which you don't see anymore. And yeah. Okay, so these blue statements are equivalent. And then now let's take the yellow statement. So Q is a sum of n squares of linear forms. Is when, of course, this, right, in the same way. So that's, and because A, B, and C are equivalent here, they are also equivalent here. Good. So now we go from A to F. From A to F. Well, now we have already here proven A implies C, and I could apply this to submatrices of M, these principal submatrices, these one, right? So because if M is PSD, it's clear that these principal submatrices are also PSD, right? Yeah, little exercise, very, very easy. Okay. And you know, if you have such a principal submatrix and you multiply it from the left and from the right with the same vector, right? Then once with a transposed vector and once with the vector itself, and just put zeros, insert some zeros in this vector and multiply the original matrix with this new vector where I have inserted a lot of zeros, right? and when this is the same. So okay, so that's quite easy. Because if this principal submatrix now is of a form a matrix transposed times a matrix, a quadratic matrix transposed to another matrix, then, because the determinant is multiplicative, so let me call this, let's say, this such a submatrix where I fix some index at I, let me call it B, when we have here, or let me call it M prime, when we have M prime equals A prime transposed A prime, where A prime is a quadratic matrix of a right size, and when the determinant of M prime is the determinant of A prime transpose times the determinant of A prime, because the determinant is multiplicative, but the determinant of a transposed matrix is the determinant itself. And so this is a square, and the square is non-negative in the Euclidean field K, right? Okay, so from A to F, it follows by applying A to C to the submatrices of M in question. Now from F to E, so let's see, so we have already from A to F, now F to E. Each coefficient of this anti-characteristic polynomial of M is a sum of certain determinants appearing in F. Aha, okay. Yes, yes, and the sum of non-negative things is non-negative. So why is this, so how are we, yes, so what are the coefficients of this determinant of M plus xin? I spoke already a little bit about it. So I write here M as, I write here M in this way, right, or coefficients. So the Aij should be the entries of M. And then it looks like the following, right? So you might have seen this already several times. So where is the determinant? It's the determinant of A11 plus X, A22 plus X, and so on up to ANN plus X. And here we have A12, A13, and so up to A1n. And here you have AN1, A21, which is the same as A12, but that doesn't matter now. I don't need that, it's symmetric now. And so on, So on the diagonal you have always these x's, you add it with x's, right? And otherwise it's just a matrix M, which you take a determinant of. How do you calculate such a determinant? Well, you can, a determinant of a matrix is the sum over all permutations, right? So, and then you take the sign of a permutation. So you choose, what do you do if you calculate the determinant? So you choose from each, you could do it in the following way. You could choose in each row an entry, and you each time choose a different entry, right? I don't know, so, right? And so on, right? So, it might happen that you choose a diagonal entry, or it might not happen, right? So the thing is that if you choose a diagonal entry, when you actually could expand further, but you could with a distributivity, you could say now, okay, actually when I choose a diagonal entry, I can choose, I have a further choice, right? Because if I really expand everything in the end, I want also with distributivity, I want also to multiply out with sum here, right? With plus here, right? So I want to you know, so whenever I choose a diagonal entry, I have actually two choices, right? That's the right way of looking this, right? I can either choose this or I can choose this, right? If I choose, for example, the top left diagonal entry, then I have a choice for this or for this. So I have an additional choice, right? Okay. And now what happens now? What is, for example, the coefficient of x to the 2 here, right? Let's see. So, I mean, I want to know about all coefficients, but for simplicity, let's look at x to the 2, for example. So in order that I get a contribution to x over 2, I need to choose 2 times something from the diagonal, namely, and actually I need to choose at least 2 times from the diagonal, and I have to choose, in fact, the x from the diagonal. So let's say I choose it here and here, right? And otherwise I don't choose any x on the diagonal. I might still choose one of these coefficients from the diagonal, right? So, but since I chose already these 2 diagonal entries, somehow the corresponding rows and columns can no longer be chosen, right? So you could, you know, because, yeah, so I cannot choose anything else in this row or column, and I cannot choose anything else in this row or column, right? So, yes, and so you see now the remaining choices are just the same choices as I have when I compute the determinant of a principal submatrix where I have deleted, so where I keep all rows and columns except these 2 which I have already deleted now, right? There is of course an issue. So one might now guess already that the coefficient here belonging to x squared is the sum overall with indices set I, such that by of cardinality n minus 2. And then here the determinant of, let me call this AI for a moment, or MI, sorry. MI of MI, right? Well, there is an issue, right? Because if you sum up these things, you have always to take into account the sign of a corresponding permutation, right? You know, determinant is the sum overall permutation, sign of a permutation, times this product, right? Okay, so, but that actually doesn't matter because the sign is exactly the same, right? So what happens actually is, like, I'm looking here at permutations which fix 2 elements, right? So because I've chosen 2 times something from the diagonal, so I look at permutations which fix 2 and which fix n in this case, right? And you know, if you have a permutation which fixes 2 elements, say 2 and n, for example, right? So I have here 1, 2, 3, 4, 5, 6. So let's say n equals 6. And 2 and 6 are fixed, right? For example, 2 and 6 are fixed. And when the others are permuted among them, right? 1 to 4, 3 to 5, 4 to 1, and 5 to 3, I guess, right? So somehow you have these 2 that are fixed, right? And now a sign of this permutation is exactly the sign, the sign of a permutation is 1 if it's a product of an even number of transpositions, and it's -1 otherwise if it's an odd product of an odd number of transpositions, right? And you see, since 2 and 6 are fixed, if I want to write this as a product of transpositions, I don't need to involve 2 and 6 in these transpositions, right? And so if somehow 2 and 6, so if I delete column 2 and column 6 and row 2 and row 6, then of course I would have to renumber now the other, 3 would become 2, 4 would become 3, and so, right? So, and for 2 or something, right? I have to shift the indices, but that doesn't matter, right? I mean, that's just a renaming, right? So, but the remaining permutation has the same sign, right? Now it was a bit short, but think about it, and when you see that actually the right formula is that you sum here from, let's say, from I equals 0 to n, and then you take here x to the I, and then you take here this, right? And that's, so let's make a sanity check that this is really okay. So let's look at the coefficient of x to the 0. Coefficient of x to the 0, which is 1, right? So that's a constant coefficient. So when I is 0 here, so I take a cardinality of I equals n, right? So this minor is just, and so I have just one term in this red sum, and this minor is just the determinant itself, because mi is just m itself. So that looks good. So I get determinant of m, and the coefficient of x to the n, that should of course be 1, right? And what do I get here? I get here that the index set is the empty set, so I get here the empty matrix, and the determinant of the empty matrix is 1, right? So that's good. Yes, you should learn to like the empty matrix. It's an important matrix. If you don't allow it, then you have a lot of case distinctions to do, and usually it's ignored in the textbooks. But if you look closely at it, then it's you should at least introduce the empty matrix, right? Otherwise, you should formulate the Cayley-Hamilton theorem only for vector spaces of dimension greater than or equal 1, and which is not a big deal, but which is an additional case distinction which you have everywhere. Then usually this problem is completely ignored. It's not a problem if you introduce the empty matrix. So the determinant of the empty matrix is 1, because the empty matrix is the 0 by 0 identity matrix, right? On its diagonal there are only ones, because there is nothing on the diagonal, because the diagonal consists of 0 entries. And now you might say, doesn't that contradict the fact that the determinant of a 0 matrix is always 0? Well, that's not true. Determinant of a 0 matrix is not always 0, because if you prove that the determinant of a 0 matrix is 0, you use the linearity in the columns over rows. But if you don't have a column or a row, you cannot use this. So then the proof doesn't go through. So the determinant of a 0 matrix is 0 if this 0 matrix is 1 by 1 or larger. But if it's a 0 by 0 0 matrix, which is the same as the 0 by 0 identity matrix, then the determinant is 1. Okay, good. Okay, so So that's the formula, and please do it as an exercise at home. And maybe another sanity check: coefficient of x to n minus 1. Here I have one by ones principal submatrices. These are just the diagonal elements in some sense, and the determinant of a 1 by 1 matrix is just the entry. So you get here the trace of M. Yeah, so this was a bit short, but yeah, but this, okay, since the coefficients are now sums of such determinants, and these determinants are all non-negative by f, then E follows. Now from E to D, this is completely trivial, because the eigenvalues are the roots of this polynomial, right? Or are the opposites of roots of these polynomials, are, you know, the negated roots of these polynomials, right? So if this polynomial has only non-negative coefficients, and actually the leading coefficient is 1, right? When it is completely trivial that it cannot have a positive root, right? So some people argue here, even with Descartes' rule. I've already seen in the literature that some people argue here with Descartes' rule of signs. They are saying, okay, there is no sign change in the coefficient sequence, right? And then and the number of positive roots is therefore 0, because it's less than or equal to the number of sign changes, and therefore there is no positive root to this polynomial, and therefore there is no negative eigenvalue, because the eigenvalues are negated roots. Okay, so but you know, it's correct, but you use part of Descartes' rule, which is completely trivial, right? Because if f has if a number of sign changes of f is 0, when the number of when it's just trivial that mu of f is 0, and you don't need Descartes' rule, although it follows formally from Descartes' rule, right? So you know, if yes, yeah, think about it, right? Because if you plug in something positive, if all coefficients are positive, then you get only positive things, but if all coefficients are negative, you get only negative things. So you will never get a positive root in this case, right? So yeah, you use trivial a very trivial case of Descartes' rule of signs, if you want. So people often cite here Descartes' rule of signs, but it's, you know, I don't think it's good, because it's really trivial. Nobody needs to learn about Descartes' rule of signs in order to prove this. So, and then E to D is trivial. So yes, and D to A. Now, because A, B, and C are already known to be equivalent, I can also go from D to A. D to A follows easily from 1, 8, 11. So maybe we should have a reminder what was 1, 8, 11. 1, 8, 11 was the following. So 1, 8, 11 was the following theorem. Let R be a real closed field. And M a symmetric n by n matrix, over R. When there exists a P invertible, a matrix P invertible over R, such that P transpose P is the identity, and P transposed MP is a diagonal matrix. That was in some sense, we called this the diagonalization as a quadratic form in matrix language here. Okay, so why can I apply 1, 8, 11? Now, so I assume that D holds. So here I can view M as a matrix over with real closure, right? And when I prove that it's even viewed as a matrix over real closure, it's PSD, right? Right. So I prove even a bit more because I prove it's even PSD over an ordered extension field, namely the real closure, right? In fact, that's equivalent, which you see here, right? Because you start here with M is PSD, and then you get to D, and from D it follows now that since this is over real closure, you get, of course, when back, you could work now over real closure, you get back that M is PSD viewed as a matrix over real closure, right? So I without loss of generality, K is now real closed, right? So, and K equals R, let's say, right? And now we have this invertible matrix, so when I don't care so much about this here, but I care about this, because on the diagonal, I care also about this, that was the diagonalization, not as a quadratic form, but simultaneously as a quadratic form and an endomorphism, remember, because P transposed is P to the minus 1, right? And because this is P to the minus 1, what I actually care about here is only the P to the minus 1. I could also write here P to the minus 1. So, and I don't care about these other things here, right? Yes, and since this is diagonal, the entries, so because I have here the P to the minus 1, you see that the diagonal entries are the eigenvalues. So I get here a diagonal matrix. If D is true, I get a diagonal matrix with non-negative entries, right? And now why is the matrix when PSD? That means the corresponding quadratic form is PSD. That means that X transpose times this diagonal matrix times X. So this is this diagonal matrix. Diagonal with non-negative entries. Non-negative entries. And I have to prove that this is non-negative for all x in R to the n. R is now k, right? And that's trivial, right? Because that is the sum over all I. If D is the diagonal matrix D1 up to the n. Xi squared. And Di with Di is are non-negative, right? Okay, good. So now we have this. And now some terminology. So let A be a commutative ring with 0 not equal 1 in order that we can build polynomial rings over it. And then let take a polynomial over A in n variables of degree at most D. And I call that constant if D equals 0. I call it linear. Also the 0 polynomial is a constant polynomial. It doesn't mean that the degree is exactly 0. It means just the degree is at most 0 here, right? I call it linear if the degree is at most 1, quadratic if the degree is at most 2, cubic if degree is at most 3, quartic if a degree is at most 4, quintic if degree is at most 5, sextic if its degree is at most 6, and so on. Right, yeah, that's just terminology. And you know, with 151 was just with notation here for polynomials of degree at most d, with notation here. And 161a was just where I defined what's a linear form, a quadratic form, cubic form, and so on, right? So it's just to compare with it. And then, yes, okay. So that was just to be able to speak better, because now we look at non-homogeneous polynomials and look at quadratic polynomials, polynomials of degree at most 2. Again, our Euclidean field. When we're following our equivalent, Q is non-negative on K to n. Q is a sum of squares of polynomials, and Q is a sum of n plus 1 squares of linear polynomials. So now our proof is very, very easy. And that's also the last thing we do today, I guess, right? Yes, the proof is very, very easy because we have already the homogeneous case. So if A is true, then I know by 2.2.6a that we homogenization is non-negative, right? And then let's go again to 2.2.6a. That was here, right? That was even over an ordered field. Here we have a Euclidean field even, right? So it doesn't matter if you look at a polynomial or its homogenization, neither for non-negativity, neither for being a sum of squares. Okay, so, and then by 2.3.2, by the homogeneous case, we have that the homogeneous thing is a sum of n plus 1 squares of linear forms. And then if I can, of course, dehomogenize, and Q is a sum of n plus 1 squares of linear polynomials. And then from C to, so A to C, C to B is trivial, and B to A is also trivial. When we are done, I just want this to be typeset in a different way. I don't want it to be italic. So I have to correct this. So many thanks for listening. Goodbye. See you next time.